Good morning or good afternoon, depending on when you watch this video. My name is Srivastava. I am Ernst & Young Distinguished Professor at the University of Kansas, and I'm going to talk about Dempster Safer Theory of Belief Functions. This framework has a lot of appeal in business world and also in area where you have uncertainties which cannot be mapped that easily under probability theory. Well, Dempster Safer theory, actually, Professor Safer is at Rutgers University. He was your former dean, or maybe still he is dean of the School of Business. Well, the outline of my presentation um, contains two different parts. Part one, Introduction to Belief Function, where I will talk about why belief functions makes more sense in a business discipline and real world problems. Then I will talk about problems with probability theory, and then compare between, I'll provide a comparison between belief functions and probability theory. Then I'll go through some of the basic concepts of Dempster-Safer theory, and then I will discuss how to combine two pieces of evidence or multiple pieces of evidence using Dempster rule of combination. And if time permits, I will talk about part two, which has to do with the evidential reasoning and business decision. Actually, evidential reasoning means reasoning with evidence. So all the different decisions are made, whether it is auditing or information systems domain, or even medical domain and legal domain, based on evidence. So what we do is we use evidence to make judgments. And the uncertainty involved in the evidence is not easily mapped using probability theory. So I will show that some of the basic definitions and show you some evidential diagram and then applications if time permits. So why belief function? Well, it seems like the real world judgments that people make seems like is easily mapped under Dempster-Safer theory of belief functions, not that easily using probability theory. So there are empirical evidence that people have done experiments. Keith Harrison was my student. He got his PhD from Kansas, and he did actually a study where he used a real piece of evidence and real subjects like auditors provided the piece of evidence and asked them which piece of evidence pertains to what assertion, and asked them questions about how much does it support the assertion or negate the assertion, or they need more information. It was interesting to see that only 20% of responses you could use probability theory to map. And under belief function, you could map 100% of that judgment. And Curley and Golden did an experiment that had to do with the murder mystery. So they had 4 suspects who may have committed the crime, and they provided different piece of evidence. One piece may have pertained to 2 different suspects, and another piece of evidence pertained to 2 different suspects, and asked them to make judgment about likelihood of who committed the crime. And they observed that the judgment that subjects were making could not be mapped using probability theory. It was easy to map using belief function framework. And plus, the other reason is that there are a lot of situations, probability like representing positive evidence or pure negative evidence. In fact, probability theory can map only mixed evidence. But in auditing domain, I know there are a lot of positive evidence that only tells you that yes, assertion is true, but nothing against the assertion. I will show you the problem using probability theory to map or represent ignorance. which also means modeling ambiguity. Also, if you really want to develop a probabilistic model, you need to have a lot of conditional probabilities. So in an environment where you have rich data, you can determine conditional probabilities. But in our domain, especially if you're looking at auditing, you don't have those conditional probabilities because you're auditing a given firm or company, and you don't have the rich data, because system is different, conditions change from year to year. So you cannot assume that if last year data tells me something, then it does not necessarily mean that it will be the same thing this year. So you don't have that conditional probabilities. And probability framework also is a special case of belief function framework. So if you have that detailed information, you could use probability theory as well, which is the same thing. And also belief function provides much more conservative estimate of risk, and we'll talk about it later on. Here is some interesting observation. Gordon and Shortliffe in 1984 were involved in developing the first computerized program, what you can call it, expert system, to diagnose common cold or common ailment. And they found that Dempster-Shafer theory seems like is much more appropriate for mapping the uncertainties they observed in the items of evidence they were gathering for their study. And they felt like, this is the right framework. So here is an excerpt from their publication. And they say that an expert uses evidence that instead of bearing on a single hypothesis in the original hypothesis set, often bears on a larger subset of this set. What it means really that in probability theory, if you have multiple possible outcomes, let's say you have 4 possible outcomes, it is required that you assign uncertainty to each state of nature, and that all has to add to 1. But under belief function framework, you don't have to necessarily assign to each state of nature. You may not have that information. You may only have information that, well, these 2 outcomes may be possible and the rest I don't know. Or maybe only one of them is possible and the rest I don't know. And so it allows a lot more flexibility to map the thought process that you observe from the value of belief function. Example 1 is an auditing example. Some of you may know that auditors use a model, conceptual model, theoretical model to plan their audit and assess risk, which is AR is the audit risk, means when auditor gives clean opinion, what is the risk that it is the financial statements really contain material misstatement. And it is a product of 4 different terms: inherent risk, control risk, analytical procedure risk, and test of detail risk. In fact, in most recent standard, which is SAS 111, they came up with combined terms called RMM, risk of material misstatement, that contains inherent risk, control risk together. And detection risk is the analytical procedure risk and the test of details. So what I'm questioning here, if you don't know this model, don't worry about it, but simply I'm trying to show you that there is a problem in the literature in terms of trying to understand the concept, what the auditors are doing, and what we interpret in terms of probability theory. The profession today, even today, says that if you do not want to depend on inherent factors, if you do not want to depend on controls, set those risks to 1. That means set inherent risk to 1, control risk to 1, and then do more detailed testing. Means I don't consider those pieces of evidence. I ignore depending on control and set that risk to 1. Then I do a lot more detailed testing. Well, there is a conceptual problem. If I set risk of material misstatement to 1, think about it. What does it mean in probability theory? If probability of some event is 1, what does it mean? That means, for sure, there is material misstatement. why the auditor will go and do so extensive test that only 5% chances are that they will miss the material misstatement. Why not go and correct the problem? That means the problem here is that the model, the way we interpret in probability theory, is suggesting that for sure you know that there is a problem. Then why auditors should go and do so much audit? And so there's a mismatch in terms of thought process. When auditors is saying that I don't want to depend on controls, I do not want to depend on inherent factors, I will set that risk to 1 and do more detailed testing. That means actually the ignorance. I just don't want to depend upon that. And so there is a basic problem here. And that is the reason actually in 92 when I wrote a paper challenging this concept, the paper was accepted in Accounting Review, that is our top journal. It becomes even a problem if you think in terms of that auditors think that, well, inherent factors are really positive, very strong, good economic environment, good management system, good controls. I will reduce that risk to half. Very strong piece of evidence that risk is not as much. So I reduce that to half. So if I set that risk to half, what does it mean? How do you interpret that a risk of material misstatement 0.5? Means chances that material misstatements are there 0.5 and no material misstatement 0.5. Well, if you interpret that in probability theory, then you run into a problem because there are two outcomes. One is saying material misstatement is there, and another one is saying material misstatement is not there and is 50-50. Well, that means they are ignorant because under probability theory, if there are only two possible outcomes, true or false, and you say 50-50, that means you are ignorant, you don't know the true state of nature. But auditor may say that no, I have definite knowledge that the risk is a lot less. And so you are not able to map their thought process under probability theory. So there is a problem. Here is an everyday example. I think you all recognize these faces, Obama and Romney. So let's go back to last election, and suppose some surveyor asked 100 people how they are going to vote. 40% committed, say that, well, I will vote for Obama, and 30% said that I'll vote for Romney, and 30% undecided. How would you express this under probability theory? Because only two outcomes here, either Obama will win or Romney will win. These are mutually exclusive. And so if I say 40% Obama, that means probability that Obama will win 40%. By definition, then Romney, probability of Romney winning will be then 60%, complement of 40%, 1 minus 40%, which is not the data is saying. Data is saying that 40% will vote for Obama and 30% for Romney and 30% undecided. And so there is a basic problem here. How do you map this thought process? And the core believer of probability theory will say, well, this 30% undecided, only two outcomes, let's distribute half and half. But that's artificial distribution. You cannot do that, or you shouldn't do that. And so under belief function, we have a term called belief mass. And so here is how basic is called basic belief mass function. And so based on the survey, M that pertains to Obama winning or getting the vote is 0.4. M, belief mass, the Romney getting the vote 30%. And either one, M, either Obama or Romney will be 30%. And so this will add to 1. So this is in contrast to probability theory. Probability theory, you are forced to assign these numbers, uncertainty, to a state of nature. Here you have two, Obama and Romney. But under belief function, you can assign to all possible combination of the state of nature. So in this case, we have Obama and Romney and Obama or Romney. And so there are some other functions that we'll define later on, but right now, if I had to say that belief based on this survey results, what is the belief that Obama will? Well, we have only one piece of evidence, this survey, and so 40% chance that Obama will, and belief that Romney will 30%, and any one of who will 1%, 100%. And there is a plausibility function that also is important function, concept that I will discuss a little bit more later on. What is the maximum uh, possible vote you can assign to Obama? Well, given 40% committed, but 30% unknown, undecided, could go all for Obama. So the maximum powerful vote that Obama could get will be 70%. And that is defined as plausibility. Plausibility function means plausibility that Obama will get the vote is 70%, and plausibility that Romney will get what percent of vote is 60%. Next, I want to compare, just conceptually very briefly, what is the difference between probability theory and belief function. The basic distribution in probability theory, you suppose you have this theta symbol. I don't know, you may feel that, what is this? This is just a theta, a representation of all possible outcomes. So I assume here that there are three possible outcomes, A1, A2, A3. For any situation, any question, there are only three possible outcomes. Then under probability theory, you assign the uncertainty to each of these state of nature. This A1, A2, A3 are mutually exclusive and exhaustive set of outcomes. And the probability on each state of nature will add to 1. And suppose you have event A, which may be a combination of A1, A2 or something. Then probability of A and probability of not A by definition adds to 1. So the important point here to note is that under probability theory, you assign this uncertainty to each state of nature, A1, A2, A3, and they all have add to 1. And then any event, probability of that plus probability of not occurring that event always adds to 1. In belief function, the difference is that you assign this uncertainty, which we call belief mass, or basic belief mass, to not only each state of nature, AI, but any combination, any 2, any 3, any 4, all of them. In our case, only 3 possible outcomes. So any individuals, any 2, and all the 3. And they all have to add to 1. So if I assign masses to all this, it will all add to 1. This A means that is these subsets, single elements, double elements, triple elements, all of them together. And so M represents the belief mass distribution function over the superset of this frame. Superset means all possible subsets of the set of elements. So A1, A2, A3 individual elements, A1, A2, A1, A3, A2, A3, and then A1, A2, A3. So that's the whole set. Dempster called this actually basic probability distribution, but I think since belief function and then bringing probability creates some confusion, so later on people started using basic belief assignment function, not a basic probability assignment function. Now, here is an example. I think I want to explain this conceptually, belief function. It is simple. You may have read it in one of the papers that you are supposed to read. It's an example of your area, Brunswick area. So I will assume that you are familiar with that. We have, let's say, cities like NB for North Brunswick, EB for East Brunswick, SB for South Brunswick, and NW for your city, New York City, and there are other cities. And I have a friend who lives in New Jersey area in this part and sends me cards. Just mails the card. So I have collected over the year, and so 10% of the cards have North Brunswick seal. Just the seal contains, and I can read it. And then 12% contain East Brunswick seal, 5% South Brunswick seal, 8% Newark seal, and then 25% have Brunswick seal that I can read, but I cannot figure out whether it is north or east or south. That part is fuzzy or just not stamped properly. So it is 25% exactly coming from this area. And the 40% have no seal of at all, any kind of seal. This whole this ellipse represents that 40% of the cards have no seal at all. So that is the exact counting of the cards. You cannot express that in probability theory. No way. How will I express that in belief function? Well, m values. And so if I have m values, so here is m for the cards coming from North Brunswick is 10%. M with the stamps East Brunswick, 12%. M for South Brunswick is 5%. M for North Newark is 8%. And then this part here that I couldn't figure out whether it is North, East, or South, that's the whole set. So M related to this set that it was mailed from this region is 25%. You can see exactly 25% cards. And then the one that has no seal, I represent that as theta, means all the elements. It could be from anywhere, 40%. So this is the exact distribution of cards that I received. Now, if I have to ask a question, what is the belief that cards were mailed from Brunswick area? Well, Brunswick area contains this cities: North Brunswick, East Brunswick, South Brunswick. And so if I say belief based on this evidence, belief that cards were mailed from Brunswick area, that means belief that it may have been mailed either from North Brunswick or East Brunswick or South Brunswick or anywhere from Brunswick. That is the belief based on this evidence. And that will be some of these values. M, that is coming from the North Brunswick, and from the East Brunswick, 12%, and South Brunswick, 5%, and these 25%, that is the whole set. So that's 52% actual count of cards that tells me that the cards were mailed from Brunswick area. Now, next, North Brunswick. Well, North Brunswick is only one direct evidence that we have mailed from Newark area. That's not Brunswick. So that is 8%. Now, plausibility, that is the concept we talked about earlier. Let's see if we now understand it clearly. Based on what cards I have collected, what is the maximum possible cards that could have come from Brunswick area? Well, this 52 definitely based on the evidence we have received it from Brunswick area, but this 40% that have no stamp could have come from Brunswick area. So if I want to see plausibility, I mean, what is the maximum possible belief that we can assign given the evidence is 52% plus 40% that could have come from there. That means 92% cards could have come from Brunswick area. There is another mathematical definition. 1 minus belief in North Brunswick is plausibility in Brunswick area. And so 1 minus 8% is exactly 92. So that's another way to do it. And here is the mathematical way to calculate plausibility. Plausibility means all those m values contained in different cities at different elements B that have non-zero intersection with A. So if I'm talking about plausibility of Brunswick, then look at all the possible elements that have non-zero intersection with B. I mean, that means A. And so North Brunswick is part of Brunswick, East Brunswick part of Brunswick, South Brunswick part of Brunswick, this Brunswick area is part of Brunswick, and then this whole unknown that contains everything is also has non-zero because Brunswick could be part of it. So that's why 10%, 12%, 5%, 25%, and then 40%, all of it has non-zero or non-empty intersection with Brunswick. That's 92%. So this is the mathematical definition, but I want to understand this conceptually, what it means to determine belief in a given set and plausibility in a given set. So just rethink about this example and see. So there is a mathematical definition of belief function, and here is the mathematical definition. Belief in A is equal to the sum of all the m values on these elements B which are contained in A. So if you take the example of our Brunswick area, A is the Brunswick area, B will be all the individual cities within the Brunswick area and the Brunswick area itself. And that's what we did. So mathematically we calculated this. And then plausibility in the similar way is this, that all the m values over the elements that have non-zero intersection with A. So if A represented our Brunswick area, then B will be all the cities in Brunswick area, the Brunswick area itself, and everything else that contains Brunswick area, like all the unknowns. And so this is mathematical definition. On minus belief of not A is always equal to plausibility of A. So this is mathematical definition. More definition, just terminology. Frame of discernment is where we look at all the possible state of nature represented by this symbol, Greek symbol theta. So these are all possible outcomes, mutually exclusive and exhaustive. That's the discernment. Focal elements is defined to be for which we have non-zero m values. So if I have non-zero m values over these two elements A1, A2, so A1, A2 is the focal element. And it is somewhere between 0 and 1. A basic probability assignment function, or the basic belief mass function, which I discussed earlier. So you can have m of all the individual elements. You can have m values for all the 2's, all the 3's, and all over the entire frame theta, and they all must add to 1. So this is by definition. Now Bayesian belief function again is a definition. Here Bayesian, it comes from the probability theory. Bayes was a probabilist. He has a theorem under his name, Bayes rule, to combine different pieces of evidence. A Bayesian belief function means that if the m values are assigned only non-zero values to single elements, then it is similar to probability theory, because in probability theory you assign probability to each state of nature, and that is it. Well, in belief function in general, you can assign belief mass to each single elements or any doubles or triples and all that. But if a situation happens where all the doubles and triples and all those m values are 0, the only non-zero values are only to the single elements, then it is just the same as probability theory. And so that's why it is called Bayesian belief function, when m values are only assigned for single elements. And it will be exactly the same. And so belief in A1 is M1 A1, belief in A2, and this becomes probability theory. And again, belief in all A's sum to equal to 1, which is like probability theory. So under this, belief and probability are exactly the same. Here is a nested belief function. Nested simply means one focal element is contained in another focal element. So a belief function is called constant belief function or nested belief function when its focal elements are nested. And so this is the nested, one circle and then the bigger ellipse actually. And so A1, A2, and then I have another set A1, A2, A3. That's the next ellipse. And then I have another set of m values, that is A1, A2, A3, A4, A5. And so if I have belief masses on these different sets, that they are called nested or consonant belief function. And non-zero values are A1, A2, A1, A2, A3, and then in all the elements A1, A2, A3, A4, A5. So you can see that the last one contains both of them, and the second one contains the first one. So this is kind of a nested. And non-nested is something like this, that you have something. So this example here, that you have some mass assigned to A, some assigned to A and B, like the what is it, pink color, and some assigned to C, that is 30%, and then blue color 20% to A, B, C, 10% to E, and 1%, 10% to just the entire set. And in terms of M values, you can see M of A is 10%, AB 20%, C is 30%, ABC 20%, M of E is 10%, and the whole set is 10%. So this is really not nested. This is a general belief function or mass distribution. Again, belief in A, using the same definition, you can say belief in ABC is belief in A, belief in AB, belief in C, and belief in ABC. This is all the non-zero elements we have. So belief in the set A is sum over all the elements that are contained in A are equal to A. So you can see A, B, C, A is contained in A, AB is contained in A, C is contained in A, and ABC equal to A. So this is the belief based on this information. And plausibility, then same way we can determine plausibility, let's say AB. So I want to look at plausibility of AB. Of course, M of A is 10% and AB is 20%. But then this AB have non-intersection, non-zero or non-empty intersection with ABC, which is this set here. So that will be 20%. So I have here A, AB, ABC, and then also with entire set A, B, C, D, E, F. So plausibility will be 10%, 20%, 20%. I think there is a typo here. This would be 10%, and then 10%, which is 60%. Okay. Representation of ignorance. Again, this is very interesting. Probability framework says that if you have only two outcomes, A is true or A is not true, then ignorance can be represented as 50-50. But in the belief function, you want to express ignorance, means complete ignorance. So I have no information about A being true and no information about A being not true. So M of A is 0, M of not A is 0, and M of A not A is 1. Or in other words, belief in A is 0, belief in not A is 0, or plausibility of A is 1, or probability of not A is 1. Simply means that I have no information that things are right, I have no information of things are wrong, or true or false. So belief in A is 0, belief in not A is 0. That's true ignorance. And in other words, plausibility that A could be true is 1, or plausibility that A could be wrong is 1, and that is again true ignorance. So this is here really true ignorance means M of A is 0, M of not A is 0. But there could be partial ignorance that we'll talk about later. If I have some small value for A to be true, some small value for A to be not true, and some value that is still we don't know, that will be partial ignorance. Belief function again versus probability theory. Probability of A is 0 represents impossibility. Belief in A is 0 simply implies that there's no evidence. So big difference between those two conceptually. Think about it. Probability that A is true is 0 implies impossible, means it is not possible that A will be true. But belief in A is 0 means I have no evidence. It's not saying that it is impossible. I have no evidence. The same thing, probability of A 1 means certainty. Definitely it is going to be true. Belief in A to be 1 also represents certainty. Means I have enough evidence to say that A is going to be true, and that is with belief 1. So both represent certainty. Probability of A plus not A is always 1, but belief in A and belief in not A could be less than 1, depends on the information, or equal to 1. Well, nature of evidence, positive evidence. So you can see if I have information where M that relates to A, that A being true is some non-zero value, let's say 0.4, and M of not A is 0. That means I have no information that A is true. Means I have no information that A is not true, in fact. That is 0. And 60% I don't know. So this is the belief function representation saying that I have positive evidence. I believe A is true with 40% level of comfort, but I don't think I have any evidence that to say that things are wrong, and remaining I don't know, I need more information. Negative evidence, same thing. I don't have any information about things being right, but I have evidence that things are wrong, weak evidence, but 30% I believe that things are wrong. 70% I don't know. So this is pure negative evidence. This is pure positive evidence. And mixed evidence will be, some for yes, some for no, some for I don't know part. So 40% believe that A is true, 10% believe is that A is not true, and 50% that could be true or not true. In probability theory, actually, mixed evidence with no ignorance is what you can map. If probability of A to be true is 40%, by definition, probability that A is not true is 60%. But you will see a lot of situations, a lot of real world situations, you will find that we have pure positive evidence. For example, suppose I have done analytical procedures, and it's looking at the ratios, trend analysis, industry numbers, gives me that the number on the books fairly presented. I cannot put too much weight because that piece of evidence is not very strong. So I can put on a scale 0 to 1, say 10%, 20%, I believe that this is fairly presented based on all these industry numbers and trend analysis and everything. But the 80%, the complementary number, I cannot say that things are wrong. But if you interpret that in probability theory, that if I say that 20% probability that this evidence tells me that this account is fairly stated, by definition 80% that it is materially misstated. But the evidence is not such where I can conclude that, because I have no information that things are wrong. I'm only saying that, well, it is reasonable to say that this account is fairly stated based on the analytical procedures I have performed. Look at the ratio, look at the trend analysis, look at the industry number, and it gives me some positive evidence that things are right. But I have no information that things are wrong. And so probability theory cannot map that thought process. The pure positive you can't express. So Dempster rule of combination is a very important concept. I want to spend some time and show you how you can combine it, because we covered the basic concept in terms of what is a belief, what is a plausibility, what is focal element, and what it means to ignorance under belief function, and then what is the difference between belief function and probability theory. And the only difference is that in probability theory you assign mass to each state of nature, but in belief function you can assign the uncertainty to all the subsets of a state of nature. And so you can assign belief mass to all the single elements, all the double elements, all the triple, and all the combination and the entire set, which adds to 1. That's the major difference. Now the question is, how do I combine multiple pieces of evidence? And so I'm going to show you a simple example, and again general enough that will help you understand some other issues. So I have 2 pieces of evidence. And here is a mathematical definition. I will wait on it. Don't worry about it, because right now this is the mathematical representation. I want to show you the intuitive reasoning behind it, and we'll work with the example and then come back, and then this will make sense. So here is the example. So I have evidence 1, 2 states, just multiple, just binary outcomes. A is true, A is not true. So this one represents A is true, and this one represents A is not true. Another piece of evidence. So let's assign the masses. So I have 40% I believe, based on evidence that I have collected, that A is true. 10% I believe that A is not true. So this is mapping on not A. And 50% I believe that either one of them could be true. That means I don't know part. So 40% I have evidence that A is true, 10% I believe that A is not true, and 50% I don't know. Then I have another piece of evidence that I want to combine. Again, two outcomes, same uh, assertion we are talking about, same set of questions. Same question, that whether A is true or not. The second piece of evidence, just some number I have cooked up. 10% I believe that A is true, 30% I believe that A is not true, and 60% I don't know. So if I have to represent these, and the question is, what is the net result? If I have two pieces of evidence pertaining to the same particular state of nature, how do I determine, what level of comfort I have or assurance I have that A is true or is not true? So, important point here to note is that these two pieces of evidence are independent. That is something important for you to note, that Dempster rule is useful or will work only when the two pieces of evidence are independent. If one depends on the other, then combining this approach will overweight the evidence, and that will not be right. So always you think of two independent pieces of evidence. And in auditing, that's what we have. We have evidence that deals with environmental factors, management attitude, integrity. Then you may have evidence about control system, that's again independent. And then you may have evidence about the test of transactions, that auditors really do detailed testing. And all different pieces of evidence have uncertainty which could be mapped under belief function. And when I want to aggregate that, I can use this approach, Dempster rule, and combine all that to get the overall belief that whether the assertion is true or not true. So you can see the evidence one, I can map M1 at A is 40%, M1 at not A is 10%, and M1 at both A1 not A is 50%. Evidence 2 is similarly 10% to A, 30% to not A, and 60% to both. How do I combine it? Well, before you combine, I think one thing that you need to think, the two pieces of evidence, there is a conflict. And conflict means if one is saying that it is true and other one is saying it is not true, that part is conflict. So there are two possible situations. If first one telling that it is true and the second evidence say it is not true, that's 40% is true and 30% not true, that's the conflict. And another part is that 10% the second evidence says that is true, but the first one says 10% is not true. So the way you combine this, that you take these M values and cross multiply. So you have 3 values here and 3 values here. So there's 9 different combinations of cross multiplication. And what we need to do is map onto a common element. So common element will map, but the conflict we need to keep it separate. And so let's first determine the conflict. So here is the conflict, only 2 different ways. The first one is saying that A is true, second one is saying A is not true. Our first one is saying A is not true, and the second one is saying A is true. So the combination, so 0.4 times 0.3 plus 0.1 times plus 1 is 0.13. So 13% is the conflict. So remaining, your 87% is what will be mapped onto genuine outcome. So let's look at now how do we combine this. So we cross multiply. Okay, renormalization. I think that's something that 1 minus conflict is renormalization, 87%. So we keep that in mind. We need that to make some adjustment on the next slide. So let's see. Here is, so we have 2 pieces of evidence, exactly the same thing we had on the other side. And I want to find what is the combined. The way we do it, so here is, again, the 2 possible outcomes, A and not A. So we cross multiply and map onto these 2 elements. I make a joke that this is something like the Sesame Street game. What are these things belong where? So you multiply 0.4. So there are 3 different numbers here, 3 different numbers. So there will be 9 numbers to map. So 0.4 times 0.1. So this to this, and the common is A. So that will go on A. So that is, you can see 3 different things, So 0.4, so that's A to A, that's first term. Then A to the whole thing, that's a common element, is still A, because the 0.6 is saying that it could be A and not A both. But this one is saying for sure A. So that will map to A. So that's 0.4 times 0.6. And then the other one is 0.5. So that I don't know part multiplies with A maps to this one. So I'm collecting all the terms through this cross multiplication that map on A. The next one, I look at all the one that maps on not A. So again, there are three terms. This not A to not A, that's 1 times 0.3, and then not A to the whole thing, and then this whole thing to not A. So that's the three of these, so 0.24. And this whole thing to whole thing, that means 0.5 times 0.6, it maps to the whole thing again, that I don't know part. So 0.5 times 0.6 is 30% to the whole thing. And this is the conflict. So they all add to 1. 33, 24, 30 plus 13, because you are taking a bunch of numbers here that add to 1, and this bunch of numbers add to 1. So when you multiply 1 to 1, it should overall product should add to 1. But the problem is that 13% is conflict. Only 87% are the values that really map it genuinely on these possible states. And so by definition, m values should add to 1. So we have to renormalize this, means divide this each of them by 0.87 to normalize it. And then it will add to 1. So the next thing is that here is the m value that is combined at A. So by definition, you can see M1A, M2A, M1A, M2 not A, not A, M1 not A, not A, M2A. So these are all possible values. So you combine it, you get 33, divide this by 87, that's the renormalization constant, not A, K minus 1. So this number is 3793. Next one is not A, so combine all the cross multiplication terms that have common element not A, and then divide that by K to make it add to 1. So this is the number 0.1 times 0.3, 0.1 times 6, 0.3 times 1, 0.3 divided by 0.87, and that is 2759. And the last one is I don't know times I don't know. So this times this, which is 0.5 times 0.6 divided by 87, that is this number. So if you add these three numbers, they will add to 1, because unnormalized was 87, and since we divided each of them 87. So this is what the mathematics is. It's not complicated. It's simply cross-multiplying terms, and then mapping it to the common element. That's what it is. And so you can see this all adds to 1. If you have more than 3 items, you can develop a spreadsheet, but I have developed some mathematical formula. If you are interested in any project, I can provide the formula. It is published work. You can write just one equation in Excel spreadsheet and combine 5, 10, 20 different items of evidence. There are programs available. I think I gave that program to business school at Rutgers in MATLAB. One can use that to combine multiple items of evidence without any problem. So we finished the first part. The second part is evidential reasoning and audit judgment. So I will go through briefly just to show you that a lot of opportunity to do some interesting work, both real world problems and research. So evidential reasoning means reasoning with evidence. And you will be surprised how much reasoning we do with evidence. So financial audit, what do? We collect evidence, we evaluate evidence, aggregate evidence, and then make judgment about whether the financial statements are fairly presented. So it's all evidence driven, means collection of evidence, evaluation of evidence, aggregation. Even other assurance, like you may be familiar, there are a lot of other assurance that are being provided, information quality, information system security, in all different kinds of assurance are provided. Same process there. You collect evidence, evaluate evidence, and aggregate evidence. So there are two aspects. One is representation of uncertainty, and we are trying to argue here that belief function provides a better framework to map that uncertainty. So that's the judgment part, evaluation part. Then aggregation part means how do we combine all these different pieces of evidence? Well, that's where the Dempster rule comes. There's a similar rule in probability theory called Bayes rule of combination. Some of you may have heard about it. And in fact, Dempster rule reduces to Bayes rule under the condition where you have information only on the single elements. So, it's equivalent to Bayes rule. So audit risk and assurance risk model help achieve the above process, means they provide a shortcut of aggregating evidence. It's very balanced. It consists of cash, accounts receivable, inventory, accounts payable, and all different items. And how do I say that financial statements are fairly presented or account is fairly presented? Well, there are some assertions, management assertions. And so if I want to say if account receivable fairly presented, when do I say? Well, there are some management assertions. The profession has developed these things. So if the account receivable exists, there is no fictitious account. If all of the account receivable are correct, and you have the right and obligations to use that asset, and it is valued properly. So these assertions, if they are true, then account is fairly presented. These are related to transaction stream, these are related to disclosure, so I'm not going to go through all these details. I'm trying to say that really you collect evidence pertaining to each assertion, and if you have enough evidence to say that now I'm highly satisfied that this assertion is true, you say, okay, this particular assertion is met, I give clear opinion. And so there's a lot of logic there, and I don't have time to discuss all those logics, but here are some evidence of reasoning. It simply means that there are different variables or assertions, and these assertions relate to some major assertions. So you can assume that this is account receivable, and these could be two different assertions. You may have evidence, rectangular box is the evidence, and so evidence provides some partial information about X being true or not true. Some piece of evidence may provide support to two different assertions or variables. And so you have evidence at all different levels, but none of them is saying that X is true or not true for sure, because they're all partial knowledge. And what this evidential reasoning means, that information flows from one variable to another variable, so all different. So the question is that what can I tell about one variable if I have partial knowledge about all the other related variables? That is what evidential reasoning is. And this can be used in medical domain. In fact, some people have done in medical domain, in a legal domain. Of course, this is where it is used also in artificial intelligence area. In fact, it is being used in anti-ballistic missiles, that you can determine the object, what it is, based on different piece of evidence. And if you combine all those different pieces of evidence and determine that the object is of this type, then you go ahead and shoot the object. So it can have a lot of appeal. So audit planning, I mentioned that this is, structure of evidence. Evidence is at all level: assertion level, account level, financial statement level. Evidence supports more than one assertion or objective. More than different accounts and overall accounts. So actually, it is a network. So here are some examples. Actually, before that, let me show you. This is a mathematical equations of accounting, that beginning balance of account receivable equal to beginning, and ending balance of account receivable equal to beginning balance of account receivable plus sales minus cash receipt. And more so, you can look at the existence of account receivable equal to beginning balance existence plus sales existence minus cash completeness. You can see the change in assertion, because existence deals with overstatement, completeness deals with understatement. If you have not completely recorded all the transactions, it will be understated. But the way the account receivable balance is related to cash receipt, if we have not recorded certain cash receipt, that implies that account receivable corresponding to that cash receipt will be overstated. So that's how the relationship is. So there's a lot of logic, that information about cash receipt, completeness, information about sales existence, information about beginning balance, related to existence, will tell me about account receivable existence. And so I have some information on the left-hand side, some information on the right-hand side, and I have to combine all this information to make a judgment overall that how much do I believe that accounts receivable is fairly stated in terms of existence, and same thing for completeness and other assertion. So it's a very complex process. And so here is one paper that talks about that particular issue, that account receivable fairly presented or not fairly presented depends on the, let's say, just two example, existence and valuation, and that valuation and existence will depend on sales existence, cash completeness. And so you have evidence at R level, and you can see how information will flow back and forth, and you can determine at each variable what is the belief that it is fairly stated and not fairly stated. Then another example, this is a real world example in healthcare industry. I worked with an accounting firm, and one of the manager who had written the audit manual for healthcare industry found it very useful. And so it's a very complex network, and we use the belief function framework to determine overall belief that accounts receivable fairly stated based on the judgment that auditor had performed the procedure. And he was pretty impressed. It didn't take much time for him to understand the basic concept, but we spent the whole day to map this, all the different assertions and related evidence, and his judgment about what level of comfort he thinks that this evidence provides to the particular assertion. So that's a pretty interesting real world example. I have used this for audit risk model. This was the paper that was published in Accounting Review. So I say, all right, now here is the financial statement, all different accounts, and then all different accounts have different assertions. So you have evidence at each level. How do you combine it? So I develop a audit risk model to show that overall financial statement will be fairly presented based on a belief function model, which really is a plausibility model. So I will not go through detail, just showing the example. This was the information system security assurance. Again, same kind of setup. How do you say that information is protected and secure? Well, information may be stolen through the internet transmission. Somebody can steal it, or information is stored on the location of the business. Maybe some customers can, genuine customers can come and take information from other customers, or maybe somebody can come and hack into the computer. So all these different assertions and related evidence. And so this is an evidential diagram for information system security. This was published in a top journal in Management Information System. Here is an example of information quality. Here is an example. Well, this is a list of papers that you can probably look for. Deals with audit risk model, fraud risk, security risk, independent risk, credit risk, all different kinds of risk. So it's pretty exciting area. Even we have used in sustainability reporting. We have a paper in process integrating statistical, non-statistical evidence that I published with Professor Schaefer. And by the way, the audit risk model in '92 was with Professor Schaefer and some of other publications too. Here are some more applications that I have developed. Application outside accounting, people have used in anti-ballistic systems. Department of Defense has used it. Bombers, remote sensing, water quality forecasting, financial portfolio management, data mining, image processing. In radiology, you get images from different sources, and same kind of uncertainty. It may not be, you cannot map it under probability theory, but under belief function, you can say that I believe 30% it is this disease, 30% this disease, rest I don't know. And then you have different kind of images with different distribution of belief masses. You can use Dempster rule to combine all that, and then you can say, well, overall belief that it is this disease is 90% and the rest we don't know. Then you can decide about the treatment. So it has a lot of merit. Let's see. Current project, we are working on several projects that is under process. And I will provide a copy of this slide so you can go ahead and read it. But thank you very much for listening, and hope you enjoyed the presentation and got something out of it about belief function. And if you have any question, please feel free to send me email or ask your instructor to contact me. I'll be happy to respond to you. It has a lot of interesting applications in the future, so it depends on your own curiosity, how much you want to get into it and apply it. But thank you all very much.